All right, let me do this and the next group of 3 questions for four total. Let me do this group of 4 questions together because they should be relatively simple Newton's second law questions. So let me just do them together. Let me write down Newton's second law as a reminder to myself and to other people who may be watching. So Newton's second law says, I guess, so sometimes you will see me write down this version, the one that says acceleration is equal to the net force divided by mass. So this is the version I use when I want to make sure the direction of causality is clear. It's the net force causing the acceleration, not the other way around. But the more popularly common form will say net force, or F, is equal to ma. Either version is fine. Sometimes, depending on the question, starting with one or the other can save just one step of algebra. Let me read this question here. It says, fireman has some mass m. He hears an alarm, slides down the pole with an acceleration a, which is less than g. So he must be applying some kind of friction force to the pole, which makes sense. Otherwise, what is the pole there for? Why not just jump down the whole story? So it says, write an equation giving the vertical force he must apply to the pole. So I find it helpful for me to draw the free body diagram to make sure I'm thinking through the situation clearly. So in this free body diagram with the fireman, there's going to be 2 forces on the fireman. Gravity pulling him down, and if that were the only force, the acceleration would have been downward at g. But that's not. There is an acceleration that's not equal to g. And so that's less than g in magnitude. So there is an upward force. Let me call this friction force. It's friction force with the pole. So, and this is also the vertical force that the fireman is applying to the pole. This is technically from pole to fireman. That's why the fire person is slowing down. But through Newton's third law, the vertical force that the fireman applies to the pole is equal to the friction labeled through Newton's third law. So I'm just going to calculate this and give that as my answer. So let me finish writing down Newton's second law equation here. The net force is, let me say the downward is positive, and that's mg minus the friction force. That should be equal to mass times acceleration. They are asking for basically this force here, so let me solve for that. The friction force should be equal to, move that over to right, move the ma to the left. It should be mg minus ma. So think that's the expression. At least if they're asking for a magnitude, positive answer. I think they are, but might be, I don't know. And they're also, you could also factor out them, but you also don't have to unless there's an instruction for you to. They are numerical equivalent. If his mass is 90 kilograms and he accelerates at 4 meters per second squared, what is the magnitude of his applied force? Yeah, let me just do that in from alpha. I can see that the mental math is going to be it's going to get annoying. So 90 kilogram, I'm going to skip all the units, keep everything in basic SI units. 90 kilogram times, I factor out the mass, 9.8 meter per second squared minus 4 meter per second squared. So that gives me 522 newtons. Probably right? Maybe. Yeah, good. All right, so that's the first question. Let me move on to the second question. I don't know how much of what I've already written will be useful, so let me just keep it until I can read the next question and see what I need to erase. A baseball catcher is performing a stunt for a television commercial. It will catch a baseball, some mass, dropped from a height of, I guess it's a stunt, because when are you dropping balls just from air? Above his mid, if his mid stops the ball in this amount of time, what is the force exerted by his mid on the ball? Okay. So I think this is a word problem. So let me first maybe start by sketching the setup. because that'll help me think through what information do I have, what kind of laws of physics do I need, what do I need to go through. So we are given this situation where a ball is being dropped from some height, assuming from like a 0 velocity down to here. There will be some sort of V final velocity of the ball going down, and at this point the catcher is gonna start catching it with the mitt, and then it's gonna move down a little more and then eventually come to stop with the V equals 0. And we are given the delta t amount of time. And what we are asked for is, looking at this portion of the interaction, we are asked for, I guess this is the picture. If I draw the free body diagram for the interaction part, there will be gravity pulling it down still, that doesn't go away, but now there's an upward applied force. And we are being asked for this upward applied force. Good. I think this is kind of the plan that's developing in my head as I'm kind of sketching this out, thinking through the information that's given. I think I'm going to need to calculate what this final speed is, because it'll be relevant in analyzing this boxed portion of the physical picture. So I will do the final velocity calculation first. This is going to be a kinematics problem. Assuming I have this final speed, then in order to get this applied force, it's going to relate to acceleration through Newton's second law. You know, that's one that says net force, which should be, I guess it's accelerating upward. So let me say the applied force minus mg is equal to mass times acceleration. So through Newton's second law, you can relate the applied force to the acceleration. So from this final speed that I somehow have from previous part, if I can figure out the acceleration, then I can figure out the applied force. Let me just do this final bit of algebra. Applied force is ma plus mg. So once I know the acceleration, I know how to do the rest of the question. Now the acceleration part, I think that's going to be another kinematics problem, because I basically have my initial speed, which is labeled V final, initial for this portion, and I have the duration of time. So from kinematics, I can say my final speed, let's say V final prime, is equal to my initial speed, which is labeled as Vf here. And I guess acceleration being upward, let me just say I'm dealing with the magnitudes minus a times delta t. So from here I can solve for acceleration. In fact, let me do that now. So acceleration, once I have this number for V final prime is just going to be 0. So once I have a number for the Vf, it's going to be Vf divided by delta t. So I think I'm almost done solving this question. All I now need is this Vf, and that's a kinematics problem from this earlier portion of the question here. And here I think we are given the height, right? We are given the height of 58 meters. So so for this kinematics problem, I think I'm gonna use the V squared formula. Mainly because I'm given all the information that relates to the V squared formula, which says V final squared is equal to V initial squared plus 2 times acceleration times delta x. So here the acceleration is g, gravitational acceleration. Assuming it's a free fall with the 58 meters, air resistance might be significant, but if I have to include that, it's unsolvable for now. So let me say g. I'm given delta x, that's just the height, h. So I can say, all right, my V final is gonna be, so V initial was 0, is from rest. So it's gonna be equal to square root of 2gh. So yeah, that's it. Now from here, you could do the rest algebraically, plug in this algebraic expression into here, and then plug that algebraic expression into here. You could totally do it. I just don't get a sense that that's going to result in any kind of simplification. So let me just build the expression in Wolfram alpha as I go. So V final, that's going to be square root of the 2 times g, 9.8 meter per second squared, times the h, 58 meters. I'm putting in the units in case I make a typo. There's an algebra error that will help me catch that. So that V final, divide by delta t, divided by 0.014 seconds. That's going to give me acceleration. With that acceleration, I multiply to the mass. And since I'm putting in the units anyway, let the Wolfram alpha do the unit conversion. 170 grams. It'll do the conversion to kilograms for me, and that plus 170 grams times 9.8 meter per second squared. So that should give me something in newtons. Hopefully, if it doesn't, I made a mistake. 411 newtons. Seems pretty high, but that's probably right. It says it's wrong. Now, so I'm 100% sure that is correct. But I can imagine someone making a programming error. And a programming error that someone could make is forgetting the gravitational force during the interaction. That'll result in an error that's bigger than 1%. 409 Newton. Wait, that's not bigger than 1%. Yeah, so I think there are two simultaneous mistakes made in the programming of the question. One, the question writer forgot about gravitational force. Two, they left it at the default tolerance of 1% instead of 0.1% instead of 1%. So I'll write to the question author to ask them to fix it. So yeah, so this is the answer that's graded as correct. But I contend my previous answer of 411 newtons is the actual correct answer. And I think once the question writer fixes both the mistakes, then both should be graded as correct, because they are, within 1% of each other. I can imagine why someone would neglect gravity here, because frankly, it is negligible. It's less than 1% influence. So both the 411 and 409 should have been graded as correct. Okay, let me go to the next question. I think that's question number 3 of the group of 4 questions we are doing. And let me start reading the question. What net external force is exerted on some mass artillery shell fired from a battleship if the shell is accelerated at... Oh, yeah. So let me just erase this, or at least partially, so that this is not confusing to people. I think I can just use Newton's second law, basically, because... we are given the mass of the shell, and I assume it's fired horizontally. So when it says I think when it says it's accelerated at this, and it does say net external force. So yeah, just the acceleration times the mass. In fact, I think I can do that in my head. Can I? Maybe. Again, trap for me. So this is 1.1 times 10 to the 3. So my power of 10 is going to 10 to the power of 7. So I need to do 2.4 times 1.1. And when I finish doing that, I think it's going to be this. E7 newtons. I think. Good. What is the magnitude of the force exerted on the ship by the artillery shell? Newton's third law. Equal and opposite reaction force will be on whatever's exerting that force. So B's answer should be same as A's answer. Yeah, good. That's question number 3. Let's look at the question number 4 and the last question in this group of 4 questions that we are doing. Again, should be questions involving simple-ish application of Newton's second law. For a swimmer who has just jumped off a diving board, assuming air resistance is negligible, the swimmer has a mass, jumps a maximum height. Oh, okay. I think I gotta sketch this more carefully to make sure I correctly understand it. It sounds like it could be a projectile-ish motion, and maybe I need to... yeah, so let me just finish erasing this, because it's a kind of a word question where you have to understand the physical picture of what's happening. So let me just take the time and sketch it out. So I have a swimmer jumped from the diving board and then reaches a maximum height somewhere here. That'll be above water. Okay, so so the height of the diving board, don't care. It's the height of the water that I care, and the height given is this height. Okay, 3 seconds after entering the water, her downward motion is stopped. Okay, there are some gaps here. Let me fill those in. People don't just hover like this. They do, come back down. So the diver is going to be entering the water here. So there's some kind of downward motion. We are not given the duration of time, but we are given the height. That's probably enough to figure out, basically, let me call this V1, the speed of the diver as the diver's entering the water. And then what it tells us is that the diver comes to a stop 3 seconds after. So this time we are given the duration of time here, and diver comes to a stop, V is equal to 0. And it's asking what is the average upward force. So upward force during this portion of the motion. So let me just blow this up and draw a free body diagram for that. While the diver is accelerating downward here, there should still be gravity on the diver. Let's hope it's included. And there will be a basically, I guess I will call it the force due to water. It's a combination of buoyancy force and the drag force. I'll just say F water. And based on those two forces, there should be an upward acceleration. And from Newton's second law, you can say that upward acceleration is result of the net force. Upward water force minus gravity is equal to mass times acceleration. They're asking for the upward water force. It ought to be mg plus ma. I think this is quite similar to the previous question. All I have to do is basically calculate the acceleration and from the given kinematics information, and once I have that, then I plug in the numbers. So let me break this problem into two parts. This portion is kinematics 1, and there's a second part. Here, I guess this box is kinematics 2. So for kinematics 1, we are given the displacement, and we know acceleration, gravitational acceleration, and we are not given time. So for a situation like that, I'm starting with a v equals 0 at the top. V squared formula is what will be most useful. V final squared is equal to v initial squared plus 2 times acceleration times delta x. Plug in the numbers that relate here. The v final is what I labeled as v1 squared is equal to initial speed 0 plus the acceleration is g, and the change of displacement is h. And because acceleration and displacement are both in the same direction, the product should be positive. So with all this, you get v1 is equal to square root of 2gh. Good, simple. Now I need to work out kinematics 2 because I need the acceleration. And for this acceleration, I think I'm using the same equation as what I used in a similar question before. So we are given the duration of time. We are not given any distance, but we know the change of velocity from here. So I guess you could say acceleration is equal to change of velocity over duration of time, or the final minus initial. I'm gonna deal with just the absolute values. So absolute value of final 0 minus initial v1 divided by the duration of time, that's 3 seconds. I'll write 3 seconds. So if I put this into calculator, I'll get a value for acceleration. And once I have that, I can plug it in here for the force on the water. Again, I could just plug in v1 here algebraically and do things algebraically, but again, nothing really simplifies, so I'll just build the numerical expression in Wolfram alpha. So I'm gonna start out with my let me actually go in the other order this time. I'll just start from here. I have my mass 80 kilogram times the gravitational acceleration 9.8 meter per second squared plus mass 80 kilogram times, this time the acceleration is going to be that, so let me write V1 for now, divide by 3 seconds. And for V1, I go back to this, square root of 2gh. So that will be square root of 2 times 9.8 meter per second squared times h, 9 meters. So I think all the parentheses match. Yeah, so this should be the upward force due to water. Now there's a slight chance it'll be graded as incorrect if the question writer forgot about the gravity here too. Yeah, so let me do a different version of this answer where we forgot about gravity. Yeah, I mean, if they asked for what is the average upward net force, then sure. But I think you really should include gravity here. So, yeah, this is a big difference this time. 354.2. Yeah, so I'll again write to the question author. What I believe is correct answer is actually this 1138 Newton. Because it is quite clear about asking for the upward force the water exerts on her. So this upward force due to water should be enough to balance gravity and then cause the acceleration. So let me make a note to write to the author. Okay, that's the last question in this group of 4 questions. Again, those little mistakes, I'll reach out to the author to get it fixed. Here, I think it actually does need to be fixed, because 1138 versus 354. I mean, you could set it up so that it grades both as correct, but I think you should learn how to account for gravity. So I think I'm right to wanting this to, just have this be the correct answer, not this.